In today's lesson, we are going to be looking at the last type of transformation, and this is going to apply to all types of functions, and that is going to be the inverse of a function. So the inverse of a function, of a function f is denoted as f negative 1. Right? So again, the function and its inverse have a property that if fa equals b, then f at negative 1, or f negative 1, b equals a. So basically we're just flipping the values. So for example, if f at 5 is equal to 13, then f negative 1 at 13 is equal to 5. Right? More simply put, the inverse of a function has all the same points as the original function, except the x and y's have been reversed. So that's the key thing. If we want to find the inverse, we're just switching the x and y values. Now, it is important to note that the f negative 1x is read as the inverse of f at x, and then negative 1 does not behave like an exponent. Right? So we want to keep that in mind, right? Similar to f at x, it's not f times x and we have to solve, right? It's just basically a different notation representing the function at a given value. Except with the negative 1, it's now read as the inverse of f at x. And to draw an inverse, all you have to do is swap the x and the y coordinates of each point. Right? So really all we're doing is just switching the x and y coordinates to make the inverse. So example 1, the table shows ordered pairs belonging to function f at x. Determine the inverse of f at x, then state the domain and range of f at x and its inverse. So for the points, all we're doing is we are just switching the values. So 0 and negative 5, 2 and negative 4, 5 and negative 3, 6 and negative 2, 7 and 0. So all we're doing is just switching them, the x and y's. Now for the domain and range, for f at x, our domain, we say x is any real number. And because it's just points, we can just list them. So negative 5, negative 4, negative 3, negative 2, and 0. For our range, same idea, but looking at the y value. So y can be any real number, given that it is only 0, 2, 5, 6, and 7. So remember, when we're dealing with points or set of points, we're just basically listing the exact values. For the inverse of f at x, same idea, except we're listing still our x values. So here we're going to have 0, 2, 5, 6, and 7. And then for our range, a little bit nicer, y, any real number, given that it is negative 5, negative 4, negative 3, negative 2, and 0. So you see the exact same thing between the two. They're just swapped, right? So our domain and our range have swapped or switched in terms of the inverse and the regular function. So looking at another example, we want to graph the function and state its inverse. So our parent function, our base function, is going to be x squared. So that's where we had the negative 3 and 9, negative 2 and 4, negative 1 and 1, 0 and 0, 1 and 1, 2 and 4, and 3 and 9. So that's our base function, right? We've dealt with the quadratic before. We should be familiar with that. The inverse of our function at x, we're going to switch. So it's going to be 9 and negative 3, 4 and negative 2, 1 and negative 1, 0 and 0, 1 and 1, 4 and 2, 9 and 3. So again, we're just switching the x and y values. We can graph that as well, just so we can visually see how it's going to look. So we'll graph our parent function first. Here is our parent function, that's our f at x. And then our inverse function will have 9 and -3, 4 and -2, 1 and -1, 0 and 0, 1 and 1, 4 and 2, and 9 and 3. So we can see our inverse function as well. So you can kind of see what it looks like, what the inverse of our quadratic looks like. Lastly, we want to state the domain and range for both. So f at x is going to equal, so our domain for our base function, our x values, x can be any real number because they extend out infinitely. Oops. And for our range, our y values can be any real number given that they are greater, they are greater than 0. For our inverse function, our domain is x can be any real number given that x is greater than or equal to 0, and our range is y is any real number. So you can see again, similar to the last example, our domain and ranges have just switched. So again, the inverse function is going to have the domain and range that are reverse of each other. So let's take a look at another one. So we're going to sketch the graph at g at x equals -2 square root -1/2 x plus 3. Then we're going to graph the inverse of that function. So first we need to graph our parent function. So our parent function, we see the square root, so our parent function we should recognize is square root x. So this is 0, we'll do 1, 4, and 9. So this is going back to our previous lessons that looked at the radical function. So our y values were then 0, 1, 2, and 3. Applying our transformations, so we can use our mapping notation if we want. So the x divided by k plus d, and the ay plus c. For our transformed function, it is going to be -2x, because we're dividing by a half, so it's multiplying. Divide by a half, it means multiply by 2, and the negative is there. There is no d value. For our y, it's -2y plus 3. Now I can apply those changes to our base function. So I get 0 and 3, -2 and 1, -8, and -1, -18, and -3. And then I can then graph the inverse. So the inverse we'll be just switching everything. So 3 and 0, 1 and -2, -1, -8, -3, and -18. Change the colors, keep it consistent. And then we wanted to graph the transformed function and the inverse of that. So I'm going to graph the purple points. So 0 and 3, -2 and 1, -8 and -1, and -18 and -3. So here's our transformed function g at x, and then our inverse of that, we're at 0 and 3, or sorry, 3 and then 0, my mistake, 3 and 0, 1 and -2, -1 and 8, or -8, and then -3 and -18. So that's our inverse of our g at x, or inverse of our transformed function. So again, inverse is just basically switching the x and y values. And looking back at these points, or at this graph and at this graph, there is something that we can notice about maybe how the inverse and the parent function are related. And so this is just a little bit of extra just to kind of look at. So the graph of the inverse of f at x is the graph of f at x reflected in the line y equals x. So this is true for all functions and their inverses. So if you can find the midpoint of each pair of points, say from example 2, and connect them, you can prove this theorem. So essentially what this is saying is if I can find those connected points, and the midpoint is always going to end up on that y at x, or y equals x line. So you see an example here, going back to that quadratic, right? So we can see, use colors. So we have one point in the middle, and we have these two that are pairs. We have these two that are pairs. These two are pairs. So I guess technically these ones are all as well because they're the same, just inverted. And if we were to draw that y at x, or y equals x line, which they've done in the second one, at y equals x, that all the points, right, are equal distance from that line. Right, so if we can find the midpoint of those 2 points, it should be a point along this y equals x line. So that's another way that we can kind of think about flipping it, but the easiest thing is just switch the x and the y's. And so for example, if I wanted to sketch the inverse of this graph, right, we could take a look and we could draw out our y equals x if we wanted to, right, and then kind of plot the points or find the midpoints between all of them. Easier way to do it though, right? So this is our parent function f at x. Let's just come up with the coordinates. So 1, 2, 3, 4, 5, 6. So negative 6, 3. Here we have negative 3, 4. Here we have negative 2, 8. We're going to plot the parent function, then it's going to switch all the values. So negative 6, 3 becomes 3 and negative 6. So 3, 1, 2, 3, 4, 5, 6. Negative 3, 4 becomes 4, negative 3. 1, 2, 3, 4, 1, 2, 3. And then negative 2, 8 becomes 8 and negative 2. So 2, 4, 6, 8, and negative 2. We can see that they are kind of equal distance from that midpoint line. If I've done it correctly, 1, 2, 3, 4, yep. So again, those are equal distance so that when if they were to connect across, right, the midpoint would be along that line. Now another thing, or another way to find the inverse is we might have to find it algebraically. So we might need to come up, okay, what is the equation for our function if we're only given the function or the kind of the equation for it. So what we have to do is we are basically going to replace the f at x with y, which is what we talked about at the beginning when we first introduced f at x, that function notation. Basically, it's just representing the y value of our coordinates. So we're going to switch or replace that with the y value, and then we're going to switch our x and y variables and then isolate for y. So we're going to solve for y, and then we're going to replace y with f at negative 1, or the inverse of f at x. So steps may not make sense right now. Let's go through and look at an example. So I'm going to replace this with y. So y equals 3x over 4. Right? We've mentioned g at x, right? Just function notation, basically the same thing as y. Let's rewrite this now. Let's switch the x and the y variables. So x equals 3y divided by 4. Now I'm going to isolate for y. So I'm going to move everything and solve for y. So I need to bring the 4 up. It becomes 4x equals 3y. Divide by 3. I get 4x divided by 3 equals y. Now that I've isolated for y, I can replace y with my inverse of the function at x. So g at negative 1x equals 4x over 3. So that is our inverse function. Let's try it for b. So y equals 4x plus 3. Now I'm going to switch the variables. So x equals 4y plus 3. Now I'm going to solve for y. So I'm going to bring the 3 over. X minus 3 equals 4y. Divide everything by 4. X minus 3 divided by 4 equals y. Okay, now I have isolated for y, so I can rewrite this. I can replace the y with h, or the inverse of h at x is equal to x minus 3 divided by 4. And we can do this with any function. So again, just replace y and then x equals x squared minus 1. Switch them, x equals y squared minus 1. Want to get the y value by itself. So move the minus 1 over. X plus 1 equals y squared. To cancel out a squared, I need to square root. So the square root of x plus 1 equals y. And now that I have it isolated for y, I can rewrite it with the inverse functions. F, the negative 1, x equals square root x plus 1. And one thing we do have to put down, though, is because it's the square root, when we take the square root of something, we actually end up with a positive and a negative version for it. So we need to be considerate of that when we square root this function. For d, again, similar idea, right? Different function, but same kind of process. So y equals 4x plus 3 divided by 5. Switch the x and the y. So x equals 4 times y plus 3 divided by 5. Now we have to solve for y. Bring the 5 up, it becomes 5x equals 4y plus 3. Move the 3 over. 5x minus 3 equals 4y. Divide everything by 4. Now that I've solved or isolated for y, I can rewrite it with the function or the inverse function notation. So the inverse of h at x is equal to 5x minus 3 divided by 4. When we're dealing with quadratic functions, or trying to find the algebraic inverse of a quadratic function, before we can interchange the x and y's, we have to work with it from a vertex form. Right? So we need to convert this function, or this quadratic function, to vertex form first before we are able to find the inverse function. So for this one, right, we're going to have to use the completing the square. So I'm going to factor a 2 out of the first two terms. So 2 and then x squared plus 8x and the plus 29 on the outside. You need to find a magic number, which is that middle number, or that second value, the 8 divided by 2 and then squared. So 8 divided by 2 is 4. 4 squared is 16. So that's that middle value. So that magic number, I have to add and subtract it. So plus 16 minus 16 plus 29. I want to move it back out of the bracket. And when I move it back out, I have to reapply that factor of 2. So x squared plus 8x plus 16 plus 29 minus 32. Now everything in the brackets should become a perfect square or a perfect square trinomial. So x plus 4 squared, and then 29 minus 32 becomes minus 3. Now that I have that, now that I have my quadratic in factored form or in the vertex form, now I can go through and rearrange it and go through the whole steps. So replace it with y. So y equals 2 x plus 4 squared minus 3. Replace the x and the y, so switch them. So x equals 2 times y plus 4 squared minus 3. Now we want to solve for y. I'm going to move the x over, or the 3 over, so x plus 3 equals 2y plus 4 squared. Get rid of the 2, so I need to divide everything by 2. So x plus 3 divided by 2 equals y plus 4 squared. I need to square root that to get rid of the squared. So the square root of x plus 3 over 2 equals y plus 4. And then move the 4 over. So we have the square root of x plus 3 over 2 minus 4 equals y. Now that I have it all isolated for y, I can reintroduce the function notation. So the inverse of f at x is equal to square root x plus 3 divided by 2 minus 4. And again, we could add the plus or minus in front of it as well. But we typically kind of only really look at the positive. So if you don't, that's okay. And the last one for the r at x equals root x plus 2. Again, rewrite the function notation, which is y. So y equals root x plus 2. Switch them. So x equals root y plus 2. Now we isolate for y. So move the 2 over. X minus 2 equals root y. To get rid of the square root, we have to square everything. So x minus 2 squared equals y. Now that I have it isolated for y, I can reintroduce the function notation, but for the inverse. So the inverse of r at x is equal to x minus 2 squared. So again, in this lesson, we've looked at the inverse, what the inverse of a function means, and how we can determine it either graphically from a table of values or algebraically from an actual function. And so again, make sure you are aware of how to do that. If you're trying to determine it from a function or a transformed function, make sure you are familiar with the transformations from the previous lessons.